中研院物理所张永贞博士，他从那个 Stony Brook 毕业以后就去 UC Riverside 做了1年半 postdoc 左右，就回到我们中研院物理所来服务。那今天他要告诉大家一些跟这个 old proton， 他特别跟我讲是这个旧的 proton 的这个故事。那我们用掌声欢迎他。
好，谢谢你的。Well, okay, I think I will give my seminar talk in English. Probably if this video is posted on the YouTube, maybe they will benefit the other part of the audience. So I give this title, well, if you are more familiar with literature, you might know The Old Man and the Sea instead of The Old Proton of the Sea. But anyway, I just quote it, just try to make you think of this title be more attractive. But the maybe more technical term I'm going to tell you is the antiquark structure of the proton. So my name is Wen-Chen Chang. I'm from 中研院物理所. Okay, so this is outline of my talk. So I would basically introduce you about the history of our understanding on the proton. First, in terms of maybe some observation, then a more theoretical interpretation actually was built based on the Quark model. Okay, and then a more fancy one is called Proton model. Maybe that is a little bit more detailed. Then, in principle, I'm looking. My research work is related with the study of the proton, which is a system of the quark inside it. And I'm involved with 3 things, 3 projects, but due to the time limit, I was basically only limited to introduce you on this study of the C-quark, which was there is an experiment in the Fermi Lab, which is in the Chicago, United States. That I would like to introduce mainly today, and then I will go to the summary. Okay, so I actually making some kind of the study, not really study, it's actually from Google. So anybody knows what the protons mean? The proton actually in the Greek means the first. So this name was actually given to the hydrogen nucleus by the Rutherford in 1920. So in that sense, that was more or less almost 100 years ago. So I guess it's kind of a milestone for people to understanding our structure. So first we have some maybe in terms of physics, we always taking the point of view like reductionism. We always saw that whenever you see something complicated, as long as we understand some substructure, we can more or less build it up, our understanding from a more fundamental structure in terms of this. So people always does, in terms, for physicists, there is always some kind of a goal. We want to look for what is the so-called fundamental degrees of freedom. So in some way, there's research like a particle physics, which is always down to the most scale, try to ask what is the most fundamental constituent of our world and what's the interaction of it. So of course, at the beginning there was this periodic table. There's people by observing this chemical property you can put into various elements in this periodical table. But over there, in some sense, you only do your observation and sorting, but you don't have an idea why all of this element has to be sitting on this family. So until this kind of a milestone experiment by Rutherford, so it's kind of a build up this kind of atomic structure, which is by nuclei and the electron circulating outside. So all of this chemical property is actually only related with this electron binding between the different elements. And all of this why all of this, actually all of these chemical elements, their physical structure is actually very similar over here. Okay, So this was really a milestone experiment, how we getting from atomic go to the subatomic cases. And then, of course, over there, Rutherford actually find out, actually he do the experiment, he find out, oh, there, at that time, the hydrogen nucleus can be found if he do some kind of the scattering. They find this fragment. They still can see this kind of hydrogen nucleus also contained in the fragments of the other nucleus. So that was kind of our start of our understanding what would be the components for nucleus. Of course, right now we understand that the inside of the nucleus, which is actually only in a very tiny, in terms of the volume, there was a very tiny fraction about the overall space of the atom, which is, however, over there, the proton and neutron was strongly confined in a very tiny space over there. Then, of course, it's starting to, another interesting question is well-known proton carry a positive charge, right? So how can this proton overcome this very strong repulsive Coulomb interaction and get themselves to be confined in such a small space? In principle, the Coulomb explosion force should be tremendous. And the whole story is actually due to neutron. Even though itself is charge neutral, but proton and neutron can have another interaction, which is now so well known in our daily life. That was called strong interaction. So strong interaction actually bind all of this neutron and the proton into a very tight structure over there. In terms of the scale, you will see here, that was typically something like a 10 to minus 14 meter. So there was 10 to minus 4, less than the so-called nano scale. So it's really very tiny over there. So in some sense, you can really imagine the strong force in terms of the magnitude is tremendous. It basically can completely overcome the Coulomb interaction force over there. Then, of course, another milestone in 1969, Gell-Mann actually, because at that time, due to the advance of the experiment, there was observed of many so-called elementary particles. At that time, all of this proton and the neutron, people more or less view them as an elementary particle. They are still, there is no structure. They just saw that there was just really a particle over there. But there are so many. So Gell-Mann actually think that there must be some kind of the substructure even below this proton and neutron. So he actually making a step further, try to modeling all of this like a neutron and a proton. At that time, there's another, maybe you are not so familiar, like a lambda or sigma, by this so-called three type of the quark. So you will see the type is like a U and a D and S. So by using three type of the quark, he making a claim they can actually like a Lego to putting this combination for three quark, they can actually explain why in a higher large structure you see all of these various hadron. However, the difficulty at that time is if you study the charge of this quark, you find out the charge is not integer of the electric charge. It's actually like U quark is the 2/3 and the D and S is 1/3. That is why Gell-Mann actually himself, he also feel quite nervous about this fact. So he in his paper he even say, okay, what I propose right now, maybe it's not true. It's only in a mathematical model, but by some kind of SU3 symmetry, it can describe our work. Okay, of course, I guess right now it's become after the discovery of the Higgs a couple years ago. I think the Heinrich group in the NTU also making a good contribution on the LHC experiment. So more or less, right now, this is our current understanding. In terms of the experimentally, we were able to verify there was on the most fundamental degrees of freedom. We know there was 6 type of the quark, and so this UDS was at the beginning was as you see, Gilman proposes. Later on, Chang quark was actually discovered by the Samuel team in the experiment in the Brookhaven. And the B quark was in the Fermi lab by Leo Lindemann. And finally, the top quark was discovered almost 20 years ago in 1995 in the Fermi lab in the PP-bar interaction. And then there's also a lot of the study on the lepton. People, I think maybe for condensed matter, you are more familiar with the electron. And then there's a more heavy type of the electron, which is muon. More or less, the property is very similar, except the mass is maybe, I think maybe 500 times more heavy than it. And then there's a tau. And corresponding, they have the neutrino of it. So, and over there, there's, here, and in terms of a large scale, we have the gravitational interaction, and then there's an electromagnetic. In terms of the quantization particle, that was the photon, and later on the weak interaction Z and W, that was corresponding to the decay, or like the flavor change, so-called flavor changing for the quark. And other than that, there in addition is the gluon. So gluon is corresponding all of this strong interaction, which is I just tell you why the proton and neutron, they will be able to form such kind of a bond state. So in some sense, we actually, and Higgs is kind of the embedded scatter field, which is how this fundamental particle, how strong they interact with the Higgs field, give the representation about how heavy they are. Let's give the explanation about the origin of the mass. So more or less from this kind of the 10 to minus 10 down to 10 to minus 12. Right now we have kind of the rough pictures how everything is. Okay, but still, so here I want to give you some kind of the puzzle, or maybe give you some kind of motivation. Okay, so here at the beginning we explain the atom. So we have the nucleus, we have the electron. So overall, the mass of the atom, you can just add the mass of the nucleus plus the mass of the electron. Okay. Then you can go into the nucleus. Nucleus, the total mass of the nucleus, you can count how many proton and how many neutron. The total mass of the nucleus is roughly the sum, also the sum of the proton, how many number of them. However, as I introduced you, nucleon. Nucleon in terms of the mass, maybe I didn't give you the mass scale. The mass scale for the proton, normally we use the MeV as the mass. So proton mass precisely is something like the 938 MeV. Of course, there's a more precise, but roughly this one. And I just tell you there's a 3 quark over there. Actually, the quark mass for this U, this proton is 3U, that is 2U plus 2D. So this individual of the quark mass for this is roughly 10 MeV. So 3 of them is at most 30 MeV. But the overall mass for proton is 938. Any idea why it's
Quark C.
Quark C? Okay. Wow, good guess. Wow. This already a C. Okay, yeah, that is how this kind of C. So in some sense, these 3 quarks, maybe when you learn the quark model, you might think this UUD, they are just like a static particle over there, static sitting there. But that is not the case. So inside it, actually, all of this quark, they actually interacted very strongly. That is why this proton was formed into the bound state. And all of this interacting, actually the interacting field is the gluon. So all of this gluon, actually, they are exchanged, all of this quark, they are exchanged or interacting with the gluon with a very large momentum. So if you looking into this famous paper by Wen-Chen from MIT, he actually put down this interesting title, Mass Without Mass. He kind of viewed this as the best illustration how this, all we learned the special relativity, M is equal, the mass equal to energy squared. So where's all this proton mass coming from? Which is actually coming from all of this high momentum gluon inside it. Okay, I see some. Okay, so this is the gluon. Maybe you are not familiar, so sorry I take a more slow step, try to introduce you. But so this quark, they actually, as I introduce you, it actually interacts with each other by exchanging the gluon. And this interaction force can be described by a so-called QCD. That was kind of a field theory, quantum chromodynamics. Okay, over there, I think this kind of interacting force has a different behavior as from our daily life. From our daily life, we more or less getting the idea from the electromagnetic interaction and also the gravitational force. So the interaction force strength will be smaller if we are more far away from each other and get more stronger if we are get close. Quite interestingly, strong strong interaction actually behave completely opposite. So when if you try to take in two quarks away from each other, the interacting strength get much increased. It's more like you can, as like a linear potential. So you can view the quark are more or less connected with some kind of a spring. So if we want to pull each other more away from each other, it will increase the interaction. So, however, the opposite things, if two quarks get closer to each other, in terms of space, they don't interact with each other. This is so-called asymptotic freedom. So this kind of the increase of the interaction when the decrease with the increase of the distance is called so-called quark confinement. So if experimentally I put into some kind of a hand, I want to pull this quark separated. So I need to pull it put a lot of force until I will never can pull out a single quark. Until my force actually, I put in force like I put in the energy. And this energy will actually create a lot of quark pair. This quark pair will bind together with the other quark and produce a lot of so-called QQ bar systems. Okay, so that is why right now, actually, even though we know the quark are the more fundamental degrees of freedom, but in terms of experimental detection, we will never see an isolated quark. We only see the quark cluster. I put this name, quark cluster. So this kind of quark cluster terminology is called hadron. Hadron then, in terms of their spin system, this is the fermion system, this is the bosonic system, that means this spin 1/2 or 3/2, and this is 0 or 1. Then you can characterize all of these things. Okay, so you are more familiar with all like proton and neutron. They are composed of the 3 quark. And On the other hand, there is a so-called meson system. For example, this pion. Pion was originally proposed by Yukawa to explain the nuclear force inside of the nucleus. And there's another like a kaon. Kaon is you replace one of it with the strangeness. Okay. So as I just introduced you, right now, even though quark, we do know they are the substructure, but we are not able to isolate it. So physicists are asking, is there any way we are able to really take out of a single quark? Unfortunately, right now, here is, I guess if you study the, if you study, so this is the so-called QCD Phase Diagram. You have the temperature of the chemical potential. So right now, quark is more or less confined in the hadron system. So there's some experimental program you are able to do is you might say that if I would be able to increase the temperature or changing this chemical potential by squeezing the nucleus, so that if I'm making two nucleons really getting itself very, very close, maybe I can cross some kind of a phase boundary. So people believe the early universe, like a very, maybe 10 to the -3 seconds or -6. Okay, our universe is kind of sitting here. The energy density is very high. So over there, indeed, the quark can be freely moving around. But right now, with the expansion of the universe, our temperature gets cooled down. So it's already across some phase boundary. It's something like the water getting into the liquid phase here. We are not able to separate two hydrogen molecules very far away, unless we really increase the temperature to make it go back to the gas system here. Okay, so for example, in the Brookhaven, they are utilizing, or in the LHC, they can actually accelerate in the heavy nucleus up to very high energy and colliding it. So over there, people expecting on a very small region, you can pump into a lot of energy, so the energy density can increase over such kind of a phase boundary. So maybe over there, you will be able to observe some kind of macroscopic volume, and where inside the quark and the gluon can actually move freely around instead of getting, it's kind of a changing the fundamental degrees of freedom from the hadron back to the quark-gluon plasma. Of course, the experimental difficulty is the quark-gluon plasma won't stay there forever. It's only happen as the intermediate state, because everything then expand and cool down again. So it's actually an experimental challenge is how can you find out the smoking gun so that you will be able to tell such kind of the collision process. Indeed, the quark-gluon plasma does happen in the middle of the collision process. So that's a difficult thing. Okay. Any question? No? Is everything clear? Sorry, I apologize. This is a little bit slow, but it's more like giving a very basic lecture. Okay. So since I tell you that the quark cannot be isolated, then you might want to ask, then why we still believe? Because normally we say to see is to believe, right? If I cannot get a quark isolated, how can I believe quark is really the fundamental degrees of more substructure of the proton, as I just tell you? Okay. Of course, this story is actually through this kind of the also a milestone work in the Stanford. They used the linear collider to accelerating the lepton go to the high energy. So by exchanging the virtual photon utilizing the electromagnetic interaction, they find out that when the momentum form so-called momentum exchange. Okay, I cannot explain more, but you are welcome. If you are interested, you are welcome to study like elementary particle physics. But basically, this Q square is more or less like the resolution. You're looking into the content of the proton. But somehow you find out with the increase of the Q square, if you increase your spatial resolution, you didn't find nothing change over there. So this kind of a form factor actually become flat over there. And this form factor is more or less corresponding to the density, or no, the spatial width over there. So that was, if you're making this form factor Fourier transformation back, you'll find out this is all actually corresponding, what you find things is a structureless, something like the delta function over there. So that is how these things was find out. Okay. So this is more or less a cartoon, give you some idea. At the beginning, you, at a low spatial resolution, you more or less view proton as overall whole. So this X, you can view, this X is actually the content, which is the carry the total, we say total momentum. So all the proton, you only can see the proton of all. Then of course the energy, the momentum is carried is 1. The fraction is 100%. Then if you gradually increase your resolution, maybe you started to see this kind of the 3 so-called valence quark. This UUD, I just introduced you, UUD. But then, so each of them, you just divide, because the mass are very close, so they are more or less 1/3 of the momentum. It's shared over there. Then, as I introduced you, they are not really static quark over there. They actually interact with the gluon. So their momentum actually have some kind of a smearing effect. So you instead of a 1/3 delta function, you're getting something like this. If you keep increasing your resolution, you're actually finding out additionally more here. So this UUD more or less corresponding to the large X we call valence quark. But if you get a smaller resolution, then you're still finding a huge component, even though their momentum fraction is very small. But their number of the density is actually quite high at the low X region here. Okay, so all of these things was experimentally you do the scattering cross-section and normalize to the so-called Mott cross-section. From here, you can extract out the so-called structure function. Okay, so now we move to our real topic, proton C. So how this C? So C is whatever you call this UUD, whatever else coming from. Okay, so of course I just introduced, inside this C, there is a gluon, which is the interacting boson for the strong interaction. And as see, you can see from this cartoon, the interesting for the gluon is when the gluon propagated, itself can actually fluctuate it into quark and the antiquark. So over here, that is our first, our very naive picture. Where's the antiquark content we're coming from? Which is actually coming from the gluon splitting. This is so-called gluon splitting. Gluon change into QQ bar, and then it can still recombine back into the gluon when it get interact with another things. Okay, so this is, if you read this Frank Close book, this